All right, so I'm going to work this final from, when was this final? It doesn't even say right here, does it? Maybe it says down here. Oh, spring 2021. Let's see if my computer agreeing with that. Yes, spring 2021. Okay. Anyway, so I'm going to work it. Don't be too confused by this first page. This was just my way of randomizing the inputs so that, and in hope to prevent cheating. I, of course, failed. People still managed to find a way to cheat, but what do you do? So anyway, so what I'm going to do is I'm going to use these inputs right here based on an imaginary student ID number of 1, 2, 3, 4, 5, 6, 7. Okay, so it doesn't really matter, just so long as the inputs are reasonable. Now, of course, be aware that this will sometimes mean that some of the numbers will be ugly. There was no effort made, obviously, or maybe not obviously, but I wasn't able to make it so the numbers would come out clean, which is always nice when the numbers come out clean. So anyway, so let's go down here. And we've got this problem, and I've entered these numbers 5 and 14 from the thing above. Okay, so I've got a cantilever, I guess not a cantilever, a beam under this particular loading, and I'm going to draw the shear and bending moment diagrams. Oh yeah, don't forget to use units. You must use a straight edge, which at this point, if you guys taking the exam, at this point you should pull out your trusty dusty ID. For me, I'm at home. I'm going to pull out my trusty dusty ruler, right? So I have several that sit around my desk for this. Okay, so the first thing that we need to do with these is I'm going to need to get B, which is going upwards, right? That's one force, and I need to get C, the vertical force at C. There's a CX here too, because this is a, what do you call that? It's a pin, right? But we're not going to worry too much about CX. Hold on, I'm going to add some background here. All right, so, CX should kind of take care of itself, right? Because we're going to do the sum of the forces in the x direction equals 0. So this is to try to get those forces. We're going to do some global equilibrium. So in the x direction, CX, well, there are no other forces. I could say plus 0, but I think we'll just call it CX because that's all the forces. Then equals 0. So because it makes my life easier, a lot of times I'll just erase that force so it doesn't confuse me later. Okay, I could sum forces in the vertical. However, I think it's pretty clear here that the vertical summation is not going to help me because there's two unknowns. So I'm going to go for the moments first, and I'll do the moments around, I think I'm going to do them around B. I can do them around B or C. Either one of those will be ideal. So let's see here. So I've got this 8 kips. So if I'm going around this point right here, I've got 8 kips going downwards, and that's going to cause a moment relative to B. That moment, it will be, well, let's see here. That will be counterclockwise, so it'll be positive, right? And its moment arm is 4 feet, right? Okay. Now I've got this 5 kips per foot going down, and that's taking place over 14 feet. So 5 times 14, so 5 kips per foot for 14 feet. I think that's 90, 70, 5 times, 70. Okay, so that's going to be 70 going down for the total effect of all of those kips per foot is 70 kips, right? And it's acting at the centroid of that rectangle, right? So it's 7 feet from this side and 7 feet from that side. Okay, so if I'm going to include that in my moment equation, then it's going to be going this way, right? And so it's going to be 70 kips, okay? And a relative to B, it's going to be creating a clockwise, so it's going to be negative. And its moment arm is going to be this 7 feet right here, right? So 7 feet. And then what else do we have here? Oh, and then we've got C. So C is going to be causing a rotation around B the opposite direction. So we're going to call that C times its moment arm, which is 14 feet, equals 0. Okay, so if we solve that equation, we're going to end up with CY, CY, right? So CY then equals, I'm getting like 32.714, totally annoying number, right? But, what do you do, right? 32.714. Okay. So if we get that, then we can get B by doing the sum of the forces in the Y. And we could say that equals 0. And let's see. So we've got 8 kips going down. Okay, I've got 70 kips going down. I've got B going up, and I've got CY going up. Right, and so B then equals, this number right here, 45.286. Okay, so to make my life easier, I think what I'm going to do is I'm going to go ahead and erase over here because there's just too much noise here, right? So let's erase all of this stuff. And then let's get back, to where we want to be. Okay, so this is a 5 kips per foot. This is 14 feet. Okay, and B, I'll go ahead and make, well, they can be in black. It doesn't matter, right? I should be able to see these, right? So B is 45.286 kips. C is, or CY, is 32.714 kips, right? And the total effect of this 5 and this 14, the total effect of this is 70 kips. And that just can be helpful to know, as we move along here. Okay, so let's start drawing our shear moment diagram. And so what we're going to do is we're going to draw these trusty lines. Okay, and everywhere where something interesting happens, we're going to draw a line. Okay, nothing interesting happens. This is kind of a nice one because there's only 3 spots where something interesting happens, and there's no applied moments. So the lack of applied moments is very nice, right? So I'm going to do my shear right here. And one of the things that I said is use units. So when we put in the shear right here, I'm going to make sure to say everything's in kips, because that way I can just put numbers and the units for the whole graph are taken care of. Okay, so I'm going to start by, I'm just going to do what it says. I'm going to go down by 8 kips. Okay, and then, so that's going to give me an 8, really a -8, I guess. And then nothing's going to happen between A and B, so this is just going to stay where it is. Right, and then I'm going to go up 45.286. So that means I'm going to go up a lot, right? 45.286. And if I started at -8 and I went up 45.286, I'm going to end up at 37.286, assuming that my numbers are correct. I feel okay about it. And then I'm going to go down 5 kips per foot over 14 feet. So I'm going to go down a total of 70. So I start at 38.286, and I'm going to subtract. Okay, so if I take 37.286 and I subtract 70, I'm going to get 32.714, a -32.714. So maybe that's like right, I don't know where that is. Maybe that's right here. -32.714 kips, because we lost 70 over that full 14, right? And then it tells us to go up by 32.714. And so we're going to get right back to 0, which is where we want to be. Okay. Now, as far as the slope of this thing, we'll note we were going down 5 kips per foot. We were going down the same amount for every foot we went to the right. Okay, so this is going to be just a nice straight line. Okay, so here we go. If I can draw that straight line, boom. Okay, so that's sweet. What we want to do now is we need to figure out the areas of these things, right? Maybe I'll pull out a different color. Maybe I'll do it in red. Okay, so the area of this first rectangle right here, well, it's got a height of -8 and it's got a width of 4, so it's going to be -32. And that is units of kips per foot. So I'm going to just put a little foot kip right there. Then I need the area of these 2 triangles. The problem with getting the areas of these 2 triangles is I don't know the base, right? So I need to know where this point is. Formally, the way to get that point is to do y equals mx plus b. So if I said shear, I'm going to assume like x equals 0 right here, even though it doesn't. It just, for this little question, it's just going to make my life a little bit easier. So v equals mx plus v naught, okay, b. So in this case, b is the y-intercept. So this is the shear when x equals 0, right? So at x equals 0, this number is 37.286, 286 at this point right here, okay, and that's in kips. The slope of this line, well, we know it right here, it's -5. Okay, and that's kips per foot times x, like that. Okay, so that's my equation, y equals mx plus b. And what I want to know is what is x? X equals what? Oh, it's not 0. X equals what when v equals 0? So I'll say, okay, well, v is 0 equals -5 kips per foot times x plus 37.286. And I'll solve that, and I'll get an x equals 7.4572. Okay, so yeah, so this drawing's a little bit bad, right? And I guess it makes sense, you know, because I drew x a little short, right? It should have been, you know, a little bit that way, a little bit to the right of there. In fact, just to make it a little bit cleaner, let's go ahead and clean that up a little bit. Okay, so I'm just going to erase this line. Like that. Okay. I don't know why I'm whispering. You know, maybe because it's finals week and I'm going delirious. Trying to, you know, get you guys as much as I can to help you. I will, you know, make a little plea that you please don't just watch my videos, that you also try as many of these as you can on your own, because otherwise you don't know what you don't know, right? Okay, so that's a better line. So this is -32.714. Okay, so that means so the x value where that thing crosses the 0 is 7. So this length right here is 7.4572. And this one on the other side over here, that's 14 minus that. Okay, like that. And then let's erase these arrows. So that should mean then that, well, we're in business, right? We're in business to get the areas of these triangles. We're just going to do 1/2 base times height. So let's see, if we pull out our trusty dusty calculator, which is kind of what we do in here, 7.4572 times 37.286. And we're going to get, it's a really annoying number. It's big. It's bad. 278.05 foot kips for that one. Oh, wait, I forgot to divide by 2, didn't I? Yeah, so forgetting to divide by 2. Remember, this is a triangle, not a rectangle. So we're going to get 139.02 foot kips. Okay, and then for the other one, we're going to do 6.5428 times 37.714. Okay, divide by 2. And I'm going to get 123.38 foot kips, right? Okay, so, and remember, this is a -123 point, whatever. Okay, so it is customary to shade these things in. I have no idea why, so I'm going to go ahead and do it, but it's not critically important. Okay, but we're just going to go ahead and do it. Okay, so once we have those, and note there are no applied moments up here. So then creating the moment diagram is just using information off of the shear diagram. Okay, so we don't even have to look up there anymore. So what I'm going to do is I'll note that there's one more point of interest than there was before. So first, let's draw our little moment here. So here's a moment, and this is in foot kips. Okay, again, remember, don't forget your units. Okay, and so there's one more point of interest, which is right in here. Okay, and so let's go ahead and see what we got to do. Okay, so I'm going to start, I guess I'll do it in blue again. We're start at 0. We're planning on ending it at 0. If we don't end at 0, we've screwed up somewhere. And in fact, I already see a screw up. Okay, and it came from bad handwriting, so be very careful with your handwriting. This should have been a 2 right here. So this number right here, I plugged into my calculator incorrectly. So let's go ahead and clean this one up and get a correct number based on the fact that, you know, my handwriting should be correct, right? So 32.714 times 6.5428 divided by 2, and we're gonna get 107. That's a much cleaner number. We like that so much more. Okay, so this number is gonna be negative 107.02. Okay, and now how did I know that that was wrong? Well, what I did was very quickly mentally, I looked at those three numbers, 32, 139.02, and negative 107, and I noted that they should add up to 0 by the time we get to the right-hand side here, and I noted that they didn't. It's fairly easy math. You know, obviously the numbers get more complicated, it's a little harder, but anyway. So we found an error anyway. So I'm going to start at 0, right? So this is a moment of 0. And then I'm just going to do these numbers, right? So I'm going to go to negative 32. So let's say this is negative 32. Okay. Then I'm going to go up 139.02. So I've got a negative 32 in my calculator. I'm going to add 139.02. Okay, and I'm going to get 107.02. So maybe that's about, I don't know, about right there, let's say 107.02. Okay, and then I'm going to go down by 107.02, so I am going to end up at 0. So I feel pretty good about that. Okay, now how do we connect the lines? Okay, and what I want you to remember here is that the value here is the slope here. Okay, so the slope of this line that I haven't drawn yet is negative 8, it's 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 negative 8. Okay, so all along there, the value of the line remains, the value up here remains negative 8, so the slope of this is negative 8. So the slope of this line is the same all the way across. Okay, it's that same negative value. Okay, all of a sudden, we now get a slope of 37 point whatever, so something pretty positive, right? So 37, so we got a slope of 37. Right? Notice that right here, I've got a value of 0, which means I've got a slope right here of 0, right? Between those 2 points, like right here, maybe I've got a value of, I don't know, somewhere in there, maybe I've got a value of 30, 20, 10. So I've still got positive slopes down here, but they're decreasing, but they're still positive, okay? So my slope is positive but decreasing, right, until it gets to a value of 0. Okay? And then at that point, I've got a slope of negative something, negative but small, right? And then more negative, and more negative, and more negative, and then I get my maximum negative slope of negative 32. Right? So this thing is going to go like this. Right? So qualitatively, that is what your graph should look like. Okay? And the points of interest, well, we've got this max point right here. We've got this min point right here. And I think those are all the points of interest. And so let's see what my question was, right? Let's see here. Draw the shear and bending moment diagrams. Be sure to label the values, important points in the diagram, and use units. And that's it. Okay? Yeah, I mean, we would probably want to erase all these little crazy arrows that I drew on here for I put them on there for explanatory purposes. You probably wouldn't want to turn it in with all of that, but it's okay. Okay? If I asked you, which I did not on this particular final, but if I were to ask you, what is the max shear and where does it happen? What is the max moment and where does it happen? What you would do is you would just kind of look at the diagram. You would say, okay, well, it didn't ask for this on this particular one, but the shear max is wherever we have the maximum absolute value, which is that 37.286. Now I always want 3 sig figs, right? So 37.3 kips. Okay, and that's happening at, usually you would say a distance from, say, A at 4 feet from A. Is usually how I would usually locate that point. Usually you don't care about positive or negative in that case. And then for moments, you might care about moment, the sign. but not yet. So for now, what you would do is you would go for the absolute value of the largest moment, which in this case is 107. We're not going to worry, we want 3 sig figs, and that's units of foot kips. And then we're going to do that at, well, from A, we're 4 plus this 7 point whatever, so we're going to be at 11.5 feet from A, right? So that was not asked, but if it were asked, that's how you would solve that particular problem. Okay, so let's scroll on down. Let's see here. Determine the location of the centroid of the region bounded by y equals kx squared, the x-axis, and blah, 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 blah. And y equals, let's see, so k here is 3, and y equals 6, and y equals 12. Okay. Okay, so if you want to do this with horizontal, so the first thing we need to do here is we need to remember our formula here is going to be maybe we should start with x bar, huh? Anyway, x bar equals the integral of x tilde dA over the integral of dA, and y bar equals y tilde dA over the integral of dA. All right, so the first thing we want to do is we want to figure out whether or not we use horizontal or vertical boxes. This is a problem where you do not want to do horizontal under any stretch of the imagination. Normally I tell you to avoid the void space. So if you can draw a box like this, you're very happy because there's no void space, right? And if you were to go horizontal, however, then the problem, so that's the one that we're gonna go with. And if you want to see it done horizontally, you can look at the key that I've posted. But if you go horizontal, the big problem is this. This section down here has a box that goes from basically 2A to A. Okay, and that's actually not very hard. What you would actually do is you would just use the rules for rectangles. However, then this one up here is defined differently, right? Because it's not always going to 2A, it's going from, this is X, and then this is 2A. So the size of that box is 2A minus X times dy. And over here, the size of the box is A times dy. So you would have to, this would be X minus 2A. So you basically have to split this up into 2 different shapes, and you'd have to do almost like a composite shape method. We're not going to do that. That's really ugly. If you want to, you can look at the key and you can solve that. I did it on the key. I choose a simpler life. I choose a mortal life. Much like what was her name? Arwen. Yes, she chose to be with Aragorn rather than to do all that nonsense, right? So I don't know if I blame her or not. I mean, he's a pretty good dude. You could do worse. Anyway, so remember the location on this line is x comma y, like that. And let's see, so it's got a width of dx. It's got a height in this case, so this is going to be y. This is going to be x. Right? So the centroid of that rectangle is right here. And it's at location x, and its height is y over 2. Okay, so that's pretty cool, right? So I should be able to work with that, okay? Maybe the first thing I'm going to do, just because it make my life easier, is I'm going to replace those. I'm going to just go ahead and solve for dA over here. So the integral of dA, so I don't have to do this twice. So the area equals that equals the integral. Okay, let's see, what's the area of this thing? It's got a, let's see, so it's length times width, so it's y dx, like that, right? And we know y equals kx squared, right? So this is going to be a equals the integral of, because I need this, the y and the dx to match, it's going to be kx squared dx, okay? And that's pretty straightforward. Should I use k or should I use 3? Let's use 3. Remember, 3 was given to me, right? Right here. So 3. Okay. So let's go ahead and do this. So area equals integral of, no, sorry, we're integrating, so we don't need that anymore. So we're going to do x cubed. Oh, nice. It works out clean like that. And then we need to know where do we start and where do we end. And so it looks like we're starting at, so this is x equals 6, this is x equals 3. Oh, no, sorry, this is 6, and this is 12, right? We were given that a was 6, right? So, so we're going to integrate that from 12 to 6, which means a is going to be rather hefty here. So let's go ahead and play. It's a 15, 12. And I don't think this has any units, so it's just going to remain like that. Okay, so that's the denominator for both of our fractions. Okay, so note that this is an unusual number, and that's what happens when you create a final where everybody gets their own answers. Sometimes somebody gets something big. It's fine. Okay, it doesn't matter. Okay, so the denominators of these things, if I wanted to, I could just, now I'm done with that, so I can just go ahead and say, okay, well, the denominators are 15, 12. And we're frozen again, so it's going to take a second. Okay, so 15, 12, 15, 12. Okay, so that way I don't have to do it twice. Okay, so now for the top here, let's go ahead and do the x bar. X bar equals the integral of, well, the x tilde is, let's see, so this location right here, I decided that x bar, y bar was equal to x and y over 2, right? So for x tilde, I'm just going to put in an x. For dA, I'm going to do it just like I did it over here, which is y dx over 15, 12, right? Since we're here, I'll go ahead and set the other one up, because after that, it's all just, you know, calculus. So we'll integrate, so the y tilde is y on 2. Okay, and then the dA is y dx over 15, 12. Okay, so now that I've done that, I don't even need the figure anymore, except to just remember that I'm going from x equals 12 to x equals 6. Okay, so let's go down here. Let's go ahead and solve this sucker. Okay, I've got that y in there, and I need everything to be in terms of x. So y equals 3x squared. Okay, so we're going to go ahead and do x bar equals integral of x times 3x squared dx over 15, 12. Okay, and let's just keep rolling, right? X equals integral of 3x cubed dx on 15, 12. Okay, x bar equals x to the 4th. This is going to be 3/4. And this is going to go from 12 to 6, divided by 15, 12. So x bar equals, so I'm getting 9.6429, okay, unitless. Okay, so over here, I'm going to go 9.64. Remember 3 sig figs, unitless, because this problem wasn't giving any units. We'll check the reasonable. Well, is that reasonable? 9.64. Well, remember we're going from 6. This is getting really sloppy over here. Let me see if I can't erase that 6 and that 12. But remember we're going from 6 to 12 here. So if I'm going from 6 to 12 in the x direction and I get like 9.6 or 9.7, that's a totally reasonable answer. Is it right? I don't know. It seems, you know, it's at least reasonable. Sorry, x equals 6 and x equals 12. Okay, so let's try in the vertical. Now the vertical is going to be a little bit harder to see if it's reasonable because I haven't figured out what this h is. But let's go ahead and get that h just to, you know, so we'll know. So to get that, we're going to say, well, what is this value up here? Well, I know the x value is 12. So to get the y value, I just have to plug it into here. So I'll say, okay, well, y equals 3 times what is x? X is 12 squared, right? So 3 times 144. So h is 432. So that's a rather large number, 432. So our expectations here, I would think it would be below half of that number, I would think. I don't know, actually. Let me see. No, it should be above half, but only barely. Wait, oh. I could see it going both ways. I could see it being above and below. It depends on the kind of on the curvature here. It's probably going to end up being below, but I guess we'll find out. But anyway, so it should be in the hundreds, right? We should not get a number like 2. Okay, that would be really weird. All right, so let's go ahead and solve this. So y bar equals, so we still got that 1512 on the bottom. I'm going to pull that 1/2 out, right? So now I get the integral of y squared dx. Okay, let's see here, this y bar, I'm going to go ahead and combine that 1/2 and that 1512, and I'm going to get 3024. Now for that y squared, I don't want y squared, I want that in terms of x because I've got an x right here. So I'm going to plug in 3x squared dx, like that. So y bar equals 3x squared, right? So what we're going to do here is I'm going to make that 9x to the 4th dx integral 3024. Y bar equals 3024. Pull that 9 out, and I've got 1/5 x to the 5th. Okay, and we're going to go from 12 to 6. Right, so it's going to be ugly, whatever it is. Okay, and that 5th power kind of gives you a feeling for the size of this sucker, or the size that it could be. So let's go ahead and just plug this in a calculator, and we'll see what we get. So sure enough, I get a number in the hundreds, 143.49. Okay, so 143. Okay, it's at least reasonable. I don't know if it's correct. In fact, it looks like it's about 1/3 of that 432. So I don't really know what to make of it. I don't know if that's correct or not, but it's at least the right process. I'm going to check my key and see if I got it correct. Yeah, and if I look at my key, then this agrees with my key. Okay, so that is it. All right, so let's roll on down. Oh, composite shapes. These are so boring. Sorry, these are not my favorite. Locate the centroid of the section y bar and determine the moment of inertia of the section around the x bar axis. Okay, so I've drawn the centroid on here for you. This particular piece of information right here was based on your student ID number, or somebody's student ID number anyway. Let's see here. Determine the moment of the shape equation can be found at the end of this document or on page 499 of your text. So this was back when students had access to their textbook. You guys do not have that, right? You have something else. You have, what do they call it? What is it that you guys have? Oh, you have your FE equations. Okay, I think there's one thing that's a little bit missing. Yeah, it seems to me we need to know this thickness right here. I'm going to go ahead and assume that that's 7 millimeters as well. I can't really see how we can do it without that information. Can we do it without that information? I don't think we can. Okay. Although it does help that they're telling us the centroid is symmetric, like it's right in the middle. So that information will basically tell us that this thing is symmetric and that has to be 7 millimeters. Anyway, so what we're going to do is I'm going to break this sucker up into shapes. And I think usually I don't like to deal with these isosceles or these non-right triangles. So normally I would break this up into 1, 2, 3, 4, like that. But however, I'm not going to do it that way because the FE equation sheet gives us the information we need to be able to solve this using a non-right triangle. So we're going to go ahead and use that formula and just see what happens, okay? And so this right here, we're going to make that 7 millimeters, okay? And so what I'm going to do is I'm going to call this top triangle 1, that's the whole thing. This will be a 2, and this will be a negative rectangle 3, okay? And so this is where we're going to draw the line for the triangle to the rectangle. Okay, so here's my shapes. Okay, and I'll go 1, 2, 3. This is going to be triangle, big rectangle, little rectangle. Okay, Let's see. So the triangle, well, the base of it is, so well, let's see, what do I need? I need to know x tilde, y tilde. I don't need x tilde, do I? I'm only looking for y bar. So let's not look for x tilde. Let's just look for y tilde. Okay, y tilde and the area, and y tilde times the area. Okay. So let's see. So on a triangle, the y tilde is 1/3 of the way up. So this distance right here is 1/3 of that 20. So it's going to be 6.6667. Okay, but its total from the origin down here is going to be 6.6667 plus this 29. So it's going to be 35,667. Okay, this is in units of millimeters. This area is in units of millimeters squared, and this is in units of millimeters cubed. Okay, so then we're going to do the area of that sucker. Well, it's got a base of 30. Right, from here to here is 30 millimeters, and it's got a height of 20. So 30 times 20 is 600, and then we'll divide that by 2. And so we're going to get 300 millimeters squared. Okay, and then to get the y tilde a, we're just going to multiply those two numbers. Okay, we'll get something like that. Okay, so now let's go ahead and do the big rectangle. Okay, I'm actually going to start marking these. These are in blue, right, because that's going to be important. Okay, so for the big rectangle, its centroid is, I'm assuming, about right here. Okay, both the big and the little rectangle, unfortunately, look like they're going to have very similar locations for their centroids. But, so it's, it's right in the middle, right? So if this is 29 millimeters, then the big rectangle has a centroid that is at half of that. So it's going to be 14.5, right? The area of the rectangle is 30 by 29. So for that, most of us would use a calculator. Did I tell you that 29 is my lucky number? I probably did not. It doesn't come up very often. Most people just don't care. So I'm going to take that 870. I'm going to multiply by 14.5, and I'm going to get 12,615. Okay? And then I need to get this, and then the last but certainly not least, I need to get this little rectangle. And remember, it's going to have a negative area, and that's going to give it a negative number right here. So if you remember to put those in there, that can help kind of save you a little bit of grief later on. Okay, and it's got a negative centroid. I think it's centroid. I think it's a little lower than that one, but I can't tell exactly, right? And so that's something that we're going to have to figure out. And let's see. It's kind of an annoying thing, right? Because we have to figure out the units on that little rectangle. And we'll notice that this is 6 right here, right? And this is 25 over here, which means that this rectangle right here, this is 19, okay? And then the width of it, well, it's not the full 30. It's the full 30 minus this 7 and that 7. So then it's going to be 16 right here. Right? It looks like I'm getting the area first. I didn't mean to do it that way, but still. 19 times 16 will give me the area. Okay, so the area of this thing is 304. Okay, if we'd gotten something larger than the area here, we should have been worried, right? So then where is that y bar? Well, it's half of this 19, right? So half of 19 is 9.5, but that's 9.5 from here. So we need to add on this extra little 6 right here. So 9.5 plus 6 is 15.5. Okay, so it looks like I drew them kind of incorrectly, right? These two should swap positions, but it doesn't matter, right? So 15.5 times 304 is going to give me a negative 4,712. Okay, so now we're all set up to, so when we want to get our y bar, we do this. Y bar equals the summation of y tilde a over the summation of the a's, right? So the summation of y bar a, it's the summation of that column. So let's go ahead and do that. 1070 plus 12,615 minus 4712. So that's 18,603. Don't forget our units. Okay, and then the sum of my areas, which is going to be 300 plus 870 minus 304. right? So we got 866. So divided by 866 millimeters squared. So this is 866. This is 18,603. Right? So our y bar equals, 1 second. Okay, 21.482. 482. Okay. Ooh, this is a typo. That should be y bar equals 21.5 millimeters. Cool. All right, so now we've got that. Okay, so now we need to get the moment of inertia. And I think on some of my other ones, remember, so the moment of inertia around the centroidal axis, a lot of time is written like this. Sometimes they'll put a bar on top of it to note that it's with respect to the centroidal axis. It has a lot of different things, but the way we solve it, it is the summation of the IXC plus AD squared, okay? And so this is the local, the moment of inertia of the thing if it was bending by itself, and this is the correction factor for the fact that it's being bent around something else. In this case, it's being bent around the global centroid and not the local centroid for that particular shape. So, so what I'm going to do here, I'm actually going to go ahead and get AD squared first. So I'm going to get D and then AD squared first, just because that's kind of, it's set up for this, right? So what we're going to do for our distances is instead of bending, say, this triangle around this location, I'm bending it around this location. So what is the distance I had to move to go from one to the other? Well, this thing was at a position 35.667, oops, 7, right? And the global centroid was at location y equals 21.482. So the distance between them, this distance, is, well, the difference. We're just going to subtract those two, right? So 35.667. So we're going to get 14.185. Okay, so that's going to go right here, 14.185, right? And so if I square that, okay, notice we're not worried about the sign on this because it's going to get squared right here. But if I square that number and then multiply times the area, I'm going to get some really big numbers. Oh, wait, so this should have units of millimeters to the fourth. It should have units of millimeters. So this will be 660,368, like that. Okay? So we're going to proceed to do that for all of these shapes, right? So for the big rectangle, 14.5. So that's, I guess that's right here. So this is up at 14.5. And we want to know the distance from 14.5 to this thing, which is at 21.482. So we're just going to subtract them. Okay, so 14.5 minus 21.482. Again, I'm not worried about the sign, so I'm not even going to bother to include it. Let's keep this all in black. 6.982. Okay, so I'm going to square that, multiply times the area right here, 870, and I'm going to get 42,411. Okay, and then we'll do it for the last one, and I'm going from this point, which is at 15.5. Again, my dots were written in the wrong location, and I want to know the distance from 15.5 to 21 point whatever. So 21.482 minus 15.5. Okay, and that's going to give me a distance of 5.982. Okay, I'm going to square it, and then I'll multiply times this area, which is 304. Okay, but notice it was a negative 304, so it's going to be a negative 10,878. Okay, boom. Okay, and then for the IXC, okay, we're basically going to look these equations up on a chart. Okay, I hate using the triangle formula, so let's go ahead and let's bring it up because Lord knows I hate it. Okay, there was probably a bit of a jump there, but anyway, so we need the formula sheet, so I've inserted it. So we need the IXC for each of these shapes. So we're going to start with the triangle. And unfortunately with the triangle, right, normally I would just split my whole thing into these two like right triangles, but that's not what we have right now. We've actually got, that's how I would do it. In this case, I didn't do it that way though. I did it with this way because this was a non-right triangle. Again, I would normally just split it into two triangles like this. Okay, but we didn't do it that way. So we just have to deal with that. So here's my formula for, oh, look, IXC. Never mind, it's easy. Never mind. I would not split this one because we're looking for IXC. If we're looking for IYC, you can see the formula gets complicated. Okay, and I would usually just split it into two right triangles because I have to do it twice, but the equation's much easier. Okay, but anyway, so we're going to use base times height cubed divided by 36. So let's go over here. So for this triangle right here, okay, the IXC for the triangle is the base of this triangle, which is 30, times the height of this triangle, which is 20, cubed, divided by 36. Okay, so the IXC for the triangle is 30 times 20 cubed, divided by 36. Okay, and that's going to be 6666.7. Okay, and that's in millimeters to the fourth. Okay, and that's, I think that's the devil's number. Okay, so if you're feeling like that's who made the test, you're probably correct. Okay, now we've got two rectangles, and the formula for a rectangle is fairly straightforward, or at least it's the one that I end up memorizing, and most of you guys will as well. So here's a rectangle. It's base times height cubed divided by 12. Okay, so where are we? So the base of the big rectangle is 30 times the height of this rectangle, which is 29, times 29 cubed divided by 12. Okay, so that's the big rectangle. So 30 times 29 cubed divided by 12 equals 6,972.5, so we're just going to call it 93. So 60,973. Okay, that is a very big number. Okay, look, it's an order of magnitude bigger than the one for the triangle. And then we need the little rectangle. Okay, so it's kind of got the same sort of formula. So it's the base of that thing is 16 right here. The height of it is 19 cubed. And then we'll divide by 12, right? So 16 times 19 cubed divided by 12 equals 9,145.3. Okay? So, so this summation is over all the shapes. And if I wanted to know the impact of an individual shape, I would add it this way. I would add these two. That would be the impact of the triangle, right? And this would be the impact of the big rectangle. And this would be the impact of removing that, that hollow space. And so I would add them all up right here. And then to get the total, I would add here. But instead, because I've got it lined up nicely, I'm just going to add here, and then I'm going to add these two, right? You can do it either way. So let's just, use our trusty dusty calculator here. Okay, so if you plug that all into your calculator, if you add all this stuff up, we're going to get 150,395 millimeters to the fourth. Okay, that's too many sig figs, right? So we're gonna simplify that by going 1.50 times 10 to the fifth. Sorry, I'll put it over here. 1.50 times 10 to the fifth millimeters to the fourth. Okay, so that's IXX prime. Sometimes there's a bar on top. Okay, something like that. Okay, so that's how we do it. Okay, note the main resistance to bending here comes from, basically it comes from the difficulty of bending this big thing right here. And then two things. One, the fact that this triangle is pretty far away from what we're bending it around. So the distance of this triangle from that centroid. And then the fact that this rectangle is not quite exactly on that that centroid. Okay. Note that hollowing this out, removing this little bit right here, okay, had almost no effect on our bending strength, right? When you consider that's about 20,000 and our grand total was 150,000. But we saved a lot of material, right? So this is why you can sometimes hollow out the middle. Okay, as long as the middle is in the centroid or close, then that shouldn't be a problem. Okay, so there you go. So that's how we solve that one. All right, last one. Okay, this ridiculous truss. Okay, so what's the trick here? Well, there is no real trick here. Let's see. It wants all the forces. So if it's all forces, I'm gonna go ahead and do this in what's the word? I'm gonna go ahead and do a method of joints because that's just what makes sense to me. You may do whatever floats your boat. Okay. So let's start by doing the global equilibrium. So I'm gonna go ahead and do it over here just because. So I'm going to do a quick and dirty free body diagram. Okay, so it looks like this. And yes, I'm going to use a straight edge because I have one, and it just makes things easier. So I've got 71 kips right here. I've got 8 feet here. I've got 6 feet here. And I've got, let's see, oh, well, I guess I could do my forces in red if I really wanted to. I've got a force F right here. I've got a force A right here, AX, and I've got a force AY right here, right? And some things about this are easy-ish, right? So if I'm looking to solve this, the easiest thing is the sum of the forces in the Y, right? Because there's only one unknown there. So I get AY minus 71 kips equals 0. So AY, noting that, again, we always expand beneath that. So AY equals 71 kips. Cool. Okay, I'm going to go ahead and draw that over here. Okay, now I need AX and F, but I can't really sum forces in the X because there's 2 unknowns. So I'm going to sum moments. So I'll do the sum of the moments around, and I'm going to choose to do that around A. Okay, because that gets rid of AY and AX. Okay, so I've got F times 6 feet, okay, and that's causing things to go counter, so that's going to be a plus. And then I've got this 71 is going clockwise, so I've got 71 kips, and its moment arm is that 8 feet, so we'll go 8 feet equals 0. Why did it have to be 71? What a horrible number. I could have made this something that divided by 3, like, I don't know, like a nice 72. And this would have worked out so much better. So 71 times 8, and then we divide by 6. And we're going to get 94.667. Okay, and that's kips. Okay, so that's F. And then the last thing I need to do is I need to get the forces, I need to get AX, right? So we'll do sum of the forces in the X equals 0. And so we'll say AX plus F equals 0. So AX equals negative 94.667 kips. Okay? So we'll go back over here, and we're going to go ahead and plug these suckers in. So AX is going this way, 94.667 kips. And F is going this way, 94.667 kips. Okay. So, all right. So now I'm going to come back and I'm going to look at this. I'm going to note that this is a 3, 4, 5 triangle. So these are all 3, 4, 5 triangles. This is 5 feet. This is 5 feet. This is 5 feet. The advantage of that is that everywhere where I want to do a sine or a cosine, like, so this angle theta is the same as this angle theta is the same as this angle theta, right? And this angle theta. Okay, so if I'm using that particular angle, then here's my triangle. And the sine of that angle theta then is this opposite, which is 3, over the hypotenuse, which is 5. Okay, so everywhere where I'm tempted to write the sine of the theta, I'm going to use 3 over 5. Everywhere where I'm tempted to write the cosine of theta, I'm going to use the adjacent 4 over the hypotenuse, 5. Okay? If you want to solve for that angle and then use it, you may. Okay? If you solve for that angle, you're going to get something like 36.870 or something. I can't remember. If you want to do that, you may. But I'm going to use 3/5 and 4/5 because it's more accurate. It means I don't have to worry about 5 sig figs, right? So let's go ahead and let's do it. And we can start anywhere we want. We just want to pick a spot that we can solve. So usually what I expect you to see here is a bunch of free body diagrams. I'm going to start at A. Okay, so let's go joint A. And it looks like this. Here's my joint. Like that, right? I've got forces. I've got this force going this way, which is 94.667 kips. And I've got this force going this way, which is 71 kips. Okay, so on this case, so this force right here is AB. And this force right here is AD. Okay, and there's almost not even a point to writing the equations here, but we'll go ahead and do it. Sum of the forces in the x equals 0. So I've got negative 94.667 kips plus AB equals 0. So AB equals 94.667 kips, right? So I drew it in tension. So AB is 94.7 in tension. So AB is 94.7 in tension. Okay, now we're going to do AD. Sum of the forces in the y direction equals 0. So I've got 71 kips going up. I'm going to subtract AD equals 0. And when I solve that, I get AD equals 71 kips. Right? And those both have positive signs on it. So they're both tension because I assumed it tension. So AD is 71 kips in tension. AD is 71 kips. And I already have the units over here, so you don't have to worry about missing that. But you do want to remember to put your little tension right there. Okay, cool. So now I know if I put this on my diagram, I know I've got this and I've got this, and this is 71 kips. And this one is going to go this way, and it's 94.667 kips. All right, so I don't want to do B because it's got 3 unknowns. I don't want to do D because it's got 3 unknowns, right? So let's not do that. And this is kind of an interesting one because it's a little bit screwy in that regard, right? I can't do A or B. I mean, I can't do B or D. So let's then go down and let's do F. Okay, because F's only got 2 unknowns. It's only got, okay, so let's do F. F. Okay, and F looks like this. Let's see here. I've got here's F. And it's got something going off this way. And it's got something going this way. And let's draw the forces. Let's put them in red. So I'm going to assume that this is in tension. And this is DF. And this is going to be EF. Right? And then I've got this force coming in this way, which is 94.667 kips. Okay. So let's go ahead and... we've got an angle right here too, theta. Okay, so let's see here. If we sum in the x direction, that's good. There's only one unknown in the x direction, right? That's EF. So let's go in the x direction. And so I've got 94.667 plus EF. And I want the cosine of that angle. And instead of the cosine of the angle, I'm going to use 4/5. So I'm going to use 4/5 equals 0. So EF equals negative 5/4 of 94.66. So I get 118.33 kips. Okay, so that's EF, and it's got a negative sign on it. So I assume tension, so it's going to be in compression. So I'm going to write 118 in compression for EF. And we'll do that in compression. Okay. Okay, so let's do DF. Okay, well, I mean, I guess I could, I'm not going to draw it on there yet. So sum of the forces into Y equals 0. Okay, so now I've got DF is going up. I've got plus EF, and it's going to be the sine of that angle. So I'm going to do times 3/5 right here, times 3/5 equals 0. Okay, now one question you might ask is, why is this plus? It's because I'm following the drawing. When I plug in for it, the sign will switch. Okay, so that's what I'm going to do right now. So I'm going to say DF plus negative 118.33 kips times 3/5 equals 0. So DF equals, okay, so multiply that by 3, divide by 5, okay, and DF is 71 kips. Okay, and it got a positive sign on it. Okay, so DF is 71 kips in tension. Okay, so cool. So let's go ahead and here, and now I've got this one's in tension, 71 kips. Okay, and this one's in compression, so we've got kind of pushing backwards, pushing out, 118.33. Okay, so now let's see. So this E still has 3 unknowns, but D we can do. Okay, so let's go ahead and do D. And if you're really clever, you can see that both of these are going to end up being 0. But we're going to go ahead and solve for that. And so let's go ahead and do that. Okay, so we're going to go ahead and do joint D. I'll do it over here so we can actually see D as I write it. So here's D. Here's D, and it's got this, it's got this thing going off at an angle theta, and it's got this thing going off at no angle, right? So let's go ahead and draw the forces that we have cut away. So I've got there's a 71 kips. I've got 71 kips. Those are almost don't even matter, right? I don't even need to draw them in my equations because they're going to cancel each other. This is going to be BD, and this one's going to be DE. Okay? So let's see here. So I'm going to do this underneath it. That way we can save some space over here. Okay, so X or Y, well, the Y only has 1 unknown, so let's do that. Sum of the forces into Y equals 0. So I've got 71 kips going up minus 71 kips going down, plus BD times the sine of that angle. And remember, everywhere where there's a sine of that angle, I'm going to do 3/5. 3/5 equals 0. Okay, and that means that if we solve that, BD equals 0. Cool. That's always nice, right? Because I don't need to do tension or compression if I get a 0. Okay, so now we need to do in the x direction. Sum of the forces in the x direction equals 0. So in the x direction, I've got BD times the cosine of that angle. For the cosine, I'm going to do 4/5 plus DE equals 0. And when I plug in BD equals 0, like that, well, I'm going to get that DE equals 0. Cool. So DE right here is 0. Cool. All right, so now this member is a big ophir. This one's a big an ophir, right? So now I can go to B, or I can go to E, or I can go to C. All of them have 2 unknowns, so it doesn't really matter which one I go to now. But B is good. Let's just do B. I don't care. They're all the same to me. So let's go ahead and do B. No, dadgummit, we don't need red. This is a black world. Those are Falcon's colors. That's no good. Anyway, so here's joint B. So it's got something going this way. Got something going this way. It's got something going this way. It's got something going that way. Okay, it's a lot of forces, but we know some of them, right? So this one's 94.667. This one is 0. So we're not even going to worry about that one. This one is unknown, but we'll call that BE. Okay, and this one right here is BC. Okay, and so that's it. Now there's an angle in there, but I don't really care about this angle, theta, because, you know, there's no force on that, so it's fine. Okay, so let's go in the x direction. So sum of the forces in the x direction equals 0, and I get negative 94.667 kips. I'm not worried about that 0 because it's a 0. I'm going to do plus BC equals 0, so BC equals 94.667 kips. Okay. Note, I assumed that it was in tension, so it is in tension, so 94.7 in tension for BC. All right, okay. Now we'll do the y direction. And in the y direction, I'm not worried about this one because it has a 0, so it's just basically negative BE equals 0. So BE equals 0. That's nice and clean. So BE equals 0. Okay, so up here on our diagram, let's see here, BE is a 0, another Ofer. So all these internal units, things were pointless. And then BC is 94.667 in tension. So it's pulling on those members right here, 94.667 kips. Okay? So that means I got one more member I got to get, which is CE. And at this point, you should be able to just look at it and tell that it's going to be 118.33. But if you can't, we just need to do one of these members. So let's go ahead and do joint E. It doesn't really matter which one you do, but I'm going to do E. I'm going to do both is what I'm going to do. But so here's joint E, and it looks like this, right? We got something coming in like this. Get something leaving like this. Those are both on the same angle, right? Theta and theta, right? And then I've got these two coming out. But those are both zeros, right? So we're not even worried about those two. And then I've got 118 going this way, 118.33 going that way. And then I've got this force right here of CE. So by observation, it should be clear that CE should be the opposite of that 118. If you don't want to do this by observation, then what you would do is you would do some forces, X or Y, doesn't matter. They both have the same information. I'm just going to do this once in the X direction. I'm not going to do it in the Y direction because it's not going to help me to do both. And so I've got 118.33 in the X direction, so that's kips. Sorry, I should be including these units all along here. Looks like I did for the other ones. And then, so if we're going in the X direction, well, we would want the cosine of that angle. So the cosine in this case is going to be 4/5. Okay. And then I'm going to add CE times the cosine of that angle, 4/5 equals 0. And if we solve for this, I'm going to get CE equals negative 118.33 kips. Boom. Right? So CE is 118.33 kips in compression. 118 kips in compression. Okay, so we have all of our answers. So we could stop right there, but if you wanted to know if you did it right, okay, and I highly recommend this if you have time, is you would do your last joint, and I'm going to go ahead and do that. So the only joint we didn't do is joint C. So what I'm going to do is I'm going to create some space here. Oh, I should write that answer on there for CE. But what I'm going to do is I'm just going to check to make sure that joint C is in equilibrium. If you get there and joint C is in equilibrium, you have to feel really good about the odds that you did this correctly. Okay, it's frozen right now. Usually when it freezes, it can hear my voice, but it can't. It just won't take my writing. It looks like it's unfreezing. So anyway, so I'm going to draw CE on here, and so it's in compression. So these two are pushing back this way, of 118.33. Okay, so to check my answer, okay, so check solution. Okay, if you have time, do the last joint. So this will be joint C, and it looks like this. And then I just need to put my forces, right? So I've got 71 kips. I've got 118.33 kips. And I've got 94.667 kips. All right. So what we'll do is we are just going to check to see if that works, right? So let's see here. Sum of the forces in the X equals 0. Okay, so I've got negative 94.667 kips plus 118.33 kips. And I need the cosine of that angle, and that's going to be 4/5. Okay, and if I plug this into my calculator, let's see here. Negative 94.667 plus 118.33 times 4/5, and I get, oh, wait, what? Oh, sorry, I should have got, I don't know what happened here, but it got all screwed up here. Let's try this again. Negative 94.667 plus 118.33 times 4/5, and we get negative 0.003 equals 0. So basically 0 equals 0. So this is cool, okay? And then let me give myself a little bit more space over here. Okay, and so then we'll check my Y forces. Okay, and I've got, looks like I've got 118.33 kips times the sine of that angle, which is 3/5. Okay, minus 71K equals 0. And we're going to plug this into the calculator, and let's see what happens. Okay, so 118.33 times 3 divided by 5 minus 71 equals negative 0.002. So basically 0 equals 0. Okay, that's the rounding error right there. Okay, so if this happens, you have to feel pretty good. Okay, if it doesn't happen, please don't erase all of your work. Please go back and just look for the error. And if you have time, redo it from scratch so that if you don't run out, so if you run out of time while redoing it, you can determine which one you want me to grade instead of having nothing. Okay. So anyway, hopefully this helps. It's 1 o'clock on Wednesday. So it's going to take me a couple hours to get this up, but hopefully I can get it up in time for you guys. Okay, so take it easy and see you. All right, bye.